Good morning. In previous sessions, we have seen the inverter, NMOS inverter design with various pull-up loads, advantages and disadvantages in each case. Now in this session, I would like to derive the inverter ratio in different situations because the inverter ratio is very important to get the symmetrical characteristics. So the situations like one inverter driven by another inverter directly and one inverter driven by another inverter through pass transistors. Generally, these are the situations. In order to get symmetrical operation, how much ratio we need to maintain, that we have to derive here. So let us see now. The case is an inverter driven by another inverter. Okay, so see the diagram. Here I am taking an NMOS inverter. This is one NMOS inverter. This is another NMOS inverter. Okay, so there is no in between these two inverters there is a direct connection. Okay, no pass transistor is existed between one inverter to another inverter. Okay, so in this case, how much inverter ratio we need to maintain, that we have to see. Okay, so to get the symmetry, the inverter voltage, inverter voltage means the voltage at which output voltage is equal to input voltage. In the characteristic curve, you can observe that one. In the inverter characteristic case, the input voltage at which both input and output values are equal, that is the inverter voltage and inverter threshold voltage. Okay, so it should be half of the VDD. It should be half of the VDD for the symmetrical operation. Okay, so to achieve this condition, how much ratio we need to maintain, or to, if you satisfy this condition, automatically you can get the symmetry, right? Okay, so in this case, in the to satisfy this condition, both the transistors of inverter operate in the saturation region, so that the current for the pull down transistor and pull up transistor is given by like this. You all know that in the saturation region, the ID current equation is IDS equal to K W by L into VGS minus VT whole square divided by 2. This is the generalized expression for the saturation current. Okay. Now apply this current to both pull up and pull down transistors. Okay. First of all, let me apply the equation to the pull up transistor. Okay. So here pull up transistor type is depletion transistor. If you see the connection in the depletion transistor case, the gate is short circuited with the source. So VGS is 0. VGS is 0. So therefore now the current is like this. IDS for the pull up transistor equal to K W pull up divided by pull up length into, since VGS is 0, just minus threshold voltage of depletion transistor, that is VTDP whole square divided by 2, right? Assume this is equation 2. Similarly, for the pull down transistor, the current equation is like this. For the pull down transistor, in case of pull down transistor, it is an enhancement transistor, and the applied voltage we are treating that the instant where the inverter voltage appears, inverter threshold voltage appears, right? That is the VGS equal to V inverse, right? So IDS equal to K WPD by LPD into, instead of VGS, write down VINV, that is inverter voltage, minus VTN, means NMOS threshold voltage whole square divided by 2. Okay, assume this is equation 3. Now Since the transistors connected in series, now the current is same in series connection. Therefore, equate equation 2 and 3, we get the equation is like this. WPD by LPD of inverter threshold voltage minus VTN whole square equal to WPU by LPU of minus VTDP whole square. Right? By equating, you can get the equation like this. Where you know that the ratio L by W is Z in VLSI notations. Right? So that is the aspect ratio. The aspect ratio L by W is represented by the notation Z. Hence, assume ZPD equal to LPD by WPD and LPU by WPU is ZPU. Okay, the aspect ratio is like this. Therefore, the above equation is with substituting the Z values like this. Then after that, if you rearrange this equation like this, square root of ZPU by ZPD of inverter threshold voltage minus VTN equal to minus of VTDP. Okay, so here finally we need to derive the inverter threshold voltage. Okay, now inverter threshold voltage equal to VTN minus VTDP divided by square root of ZPU by ZPD. The equation comes like this after different rearrangements. Now substituting the typical values for each and every voltage, that is, VTN is 0.2 times of VDD. That is the typical value for the NMOS threshold voltage. Enhancement NMOS threshold voltage. Typical value is 0.2 times of VDD. For the depletion MOS transistor, it is minus 0.6 times of VDD. And inverter threshold voltage 0.5 times of VDD. So substitute all this, and finally if you derive, the ZPU by ZPD comes like this, 4 divided by 1. This is the inverter ratio. This is the inverter ratio, that is 4 by 1 we have to maintain. That is the ZPU of inverter is 4 times of ZPD. Okay, where what is ZPU? L by W ratio of pull-up transistor is equal to 4 times of L by W of the pull-down transistor. So if that much aspect ratio, if you maintain, you can satisfy the inverter threshold voltage is equal to half of the VDD. So symmetricity we are getting. Okay, so that what happens, if the symmetricity, if you get the symmetricity, you can avoid the degradation of voltage levels. That is the importance behind this concept, right? Thank you. In the next class, we can see how much inverter ratio we have to maintain if the inverter driven by another inverter through pass transistors. That we can see in the next class, right? Thank you.